In a previous video, I described this apparatus to measure the electron charge to mass. The E over M apparatus consists of coils that create a magnetic field, and that magnetic field applies the Lorentz force on moving electrons, as shown in the diagram on the right here. And the velocity of the electrons is always perpendicular to the magnetic field because the velocity is in the plane of the page here, and the magnetic field is going into the page. And so if we look at the Lorentz force, which is the charge times the charge velocity cross product with the magnetic field, we can rewrite that as the magnitude is just QVB times the sine of the angle, and the angle is 90 degrees, so it's just QVB because sine of 90 is 1. So we'll come back to that shortly. We want to first calculate the magnetic field from the parameters of the instrument. So there's the current readout from the coils, and so we need to figure out how to calculate the magnetic field for that set of coils. So there are two coils, and if we were to look at them from above, they would look something like this, where the glass bulb is here in the middle. And just for simplicity, I'm going to remove the bulb. And in the center of the bulb is where the electrons are forming this circle, and that is a distance that is 8 centimeters from the coil itself on both sides. So we call that Z, the distance along the axis, which would be 0.08 meters. The diameter of the coils, according to the manufacturer, is 30 centimeters. But when I measured, they were closer to about 28.5. So I'm going to use the experimental measure for this calculation and just put 28.5. And so if we write down our experimental settings, there are 130 turns in each coil. There are two coils. The coils have a radius of 14.25 centimeters, and the position of the charge that's being affected by the magnetic field of the coils is 8 centimeters away from the coil. And so we did an experiment where we set the accelerating voltage for the electrons at 300 volts, that will come up later, and the current to create the magnetic field was 2.6 amps. And we know that the magnetic field for a single coil is mu naught over 4 pi 2 pi r squared times the current divided by c squared plus r squared to the 3/2. And so if we plug in our numbers, and I'm going to write this as a magnitude so we don't have to worry about, we know the direction from the setup of the experiment. And so if we plug in numbers from all of this, so we have 2.6 amps for I, R is 14.25 centimeters, Z is 8 centimeters, we have to convert those things. But if we plug all of those numbers in and we multiply by the number of turns and two coils, then we have to, so I would call that 1 and 1. One coil, one turn. We would have to multiply 130 times 2, because the coils have a current that make the field additive, multiplied by the one turn, one coil magnetic field. And if we calculate that for these parameters, we get 0.001976 Tesla. So now we know the magnetic field. What we want to do is figure out how we can use this force equation to calculate the electron charge to mass ratio. So what we want to recall is that from Newton's second law, the force that's created from the coils is going to equal the mass times acceleration that we observe, and what we observe is circular motion. So that's the mass of the electron, its velocity squared, or speed squared in this case, divided by the radius of the circle that's formed for the electrons, because they're the electrons are what are traveling in a circle. And so then this force from the coils is the Lorentz force that we know as QVB. That equals the circular motion that we observe. And if we move things around, what we're trying to do is get charge over mass. So I move the B over to the bottom, I move the V over to the bottom, which cancels 1, and then I move the M over, so that gives me that. Now, what we have to realize, though, is that the velocity of the electrons has to do with the accelerating voltage. And so if we recall, the potential energy that is created by an electric potential so we did this in class already, but Q delta V is going to equal to, that's the potential energy, and that's going to be equal to the change in kinetic energy, which, if the electrons start out at rest, will just be their final velocity. And so then we can simplify this to solve for V so that we're able to plug it back into that equation up above. So I'm going to solve for V is equal to the square root of Q delta V, that's the change in potential, over 1/2 m. Or I could write that as 2Q delta V over m. And you'll notice that there's a Q over m in that, so we're going to have to deal with that and when we plug it back in. So we have Q over m is equal to the square root of 2Q delta V over m times 1 over BR. So I'm going to square both sides. And then I'm going to move all the Q's over M's to one side so that I'll get Q over M is equal to 2 delta V over BR squared. And in this case, Q is equal to the electron charge. But we're going to just deal with magnitudes here because the direction of everything is constantly changing as the electron goes around in a circle. And so we can just think of this as the magnitude of E over M is 2 times delta V over B R squared. And if I plug in the parameters that I have from above, that's 2 times 300 volts divided by 0.001976 Tesla. And the radius of the circle that the electron is making when these are the parameters is 3 centimeters. And when I calculate all of those things, I get 1.71 times 10 to the 11 coulomb per kilogram. Now, what we expect would be the charge of the electron over the mass of the electron. Which I believe, let's see, I'm gonna have to pull up a calculator.
Working?
$1.76.